رحمة للعالمين.
Thank you. Thank you. So still somewhat slow, though. How, though, can we perhaps do a little better fundamentally? So we can do so if we introduce yet another technique. And this one isn't so much a function of code as it is concept. And it's something that you might have seen in the real world, but perhaps not so obviously so. So it turns out in programming, recursion refers to the ability of a function to call itself. In the world of mathematics, if you have a function f, if f appears on both the left side and the right side of a formula, that would be a recursive function in the math world too. Whenever f is defined in terms of itself, or in our case, in programming, anytime a function calls itself, that function is said to be recursive. And this is actually something we've seen already in class, even though we didn't call it as much. So for instance, consider this pseudocode from earlier, whereby this was the pseudocode for searching via binary search. A whole bunch of doors. If no doors are left, return false. That was the additional conditional we added. But then if number behind middle door, return true. And here's the interesting part. If number is less than middle door, search the left half. Else, if number is greater than middle door, search the right half. This pseudocode earlier was itself recursive. Why? Because here is an algorithm for searching. But what's the algorithm telling us? Well, on this line and this line, it's telling us to search something else. So even though it's not explicitly defined in code as having a name, if this is a search algorithm, and yet the search algorithm is using a search algorithm, this pseudocode is recursive. Now, that could quickly get you into trouble if a function just calls itself again and again and again. But why intuitively is it not problematic that this code, this pseudocode, calls itself? Why will the algorithm still stop? Yeah. Exactly. It has some exit condition, like if no doors less. And more importantly, anytime you search the left half, you're searching a smaller version of the problem. Anytime you search the right half, you're searching a smaller version of the problem, literally half the size. So this is why in the phone book, obviously, I couldn't tear the phone book in half infinitely many times, because it was literally getting smaller each time. So recursion is this ability to call yourself, if you will. But what's important is that you do it on a smaller problem, so that eventually you have no more problems to solve, or no more data, no more doors at all. So these two lines here would be the recursive elements here. But if we go back to week 0, we could have used recursion in some other way. So this was our pseudocode for the phone book back in week 0. And recall that we described these yellow lines as really representing a loop, some kind of cycle again and again. But there was a missed opportunity here. What if I had re-implemented this code to do this instead? Instead of saying open to middle of left half of book and then go back to line 3, like literally inducing a loop, or open to middle of right half of book and go back to line 3, inducing another loop, why don't I just recognize that what I'm staring at now is an algorithm for searching a phone book? And if you want to search a smaller phone book, like A through M or N through Z, we'll just use this same algorithm. So I can replace these yellow lines with just this, casually speaking. Search left half of book, search right half of book. This would be implicitly, and now I can shorten the whole thing, a recursive implementation of the phone book pseudocode from week 0. And it's recursive because if this is a search algorithm and you're saying go search something else, that's fine. That's recursive. But because you're searching half of the phone book, it's indeed going to get smaller and smaller. Even in the real world, or the real virtual world, you can see recursive data structures in the wild, or at least in Super Mario Brothers like this. Let me get rid of all of the distractions here and focus on this pyramid, where you have 1 block, then 2, then 3, then 4. Well, this itself is technically recursively defined in the sense that, well, what is a pyramid of height 4? Well, it's really what? How would you describe? A pyramid of height 4 is actually the same thing as a pyramid of height 3 plus 1 additional layer. Well, what's a pyramid of height 3? Well, it's technically a pyramid of height 2 plus 1 additional layer. And so even physical structures can be recursive if you can define them in terms of itself. Now, at some point, you have to say that if the pyramid is of height 1, there's just 1 block. You can't forever say it's defined in terms of a height -1, -2. You would never stop. So you have to kind of have a special case there. But let's go ahead and translate something like this, in fact, to code. Let me go back to VS Code here, and let me implement a program program called iteration that refers to a loop iterating. And let me implement a very simple pyramid like that. So let me go ahead and include the CS50 library. I'll include our standard io.h, int main void, no command line arguments today. And let's go ahead and do this. Let's declare a variable called height, ask the human for the height of this pyramid. And then let's go ahead and draw a pyramid of that height. Now, of course, draw does not yet exist, so I'm going to need to invent the draw function. Let me go ahead and define a function that doesn't have a return value. It's just going to have side effects. It's just going to print bricks on the screen, call draw, and it takes in an integer n as its input. And how am I going to implement this? Well, again, I want to print 1 block, then 2, then 3, then 4. That's pretty straightforward, at least once you're comfortable with loops. Let me go back to the code here. Let me go ahead and say for int I gets 0, I is less than n, I plus plus. And that's going to iterate essentially row by row. And on each row, I want to print out 1, then 2, then 3, then 4 bricks. But I'm iterating from 0 to 1 to 2 to 3. So I think that's OK. I can just say something like for int j gets 0, j, let's be clever about this, is less than I, j plus plus. And now let me go ahead and inside of this loop, I think I can get away with just printing out a single hash sign. But then outside of that loop, similar to last week, I'm going to print my new line separately. So a little non-obvious at first, but this outer loop iterates row by row, line by line, if you will. And then the inner loop just makes sure that when I equals 0, let's see. Oh, nope, there's a bug. I need to make sure that it's j is less than I plus 1. So when I is 0 on my first line of output, I'm going to print out 1 brick. When I is 1, I'm going to print out 2 bricks, and so forth. So let me go ahead and run make iteration. All right. And now seems to compile. Uh-oh. Implicit declaration of function draw. So I'm making week 1 mistakes again. What? Say again? Yeah, the prototype is missing. I didn't declare it at the top. That's an easy fix, and the only time really it's OK and necessary to copy paste. Let me copy the function's declaration there, end it with a semicolon, so that Clang now knows that draw will exist. Make iteration. Now it works. Thank you. /iteration. We'll type in something like 4, and there we have it. Our pyramid of height 1, 2, 3, 4 that looks pretty similar to this, albeit using hashes. So that's how we would have implemented this like 2 weeks ago in week 1, maybe last week, but just using arrays. But let me propose that we could do something recursively instead. Let me close this version of the code, and let me go back to VS Code and open up recursion.c just to demonstrate something recursively. And I'll do it incorrectly deliberately the first time. So let me include CS50.h. Let me include standard io.h. Let me do int main void. And let me just blindly draw a pyramid initially of height 1. But now in my draw function, let me re-implement it a little differently. So my draw function this time is still going to take a number n, but that's how many hashes it's going to print. So let's do for int I gets 0, I is less than n, I plus plus. Then let's go ahead and print out a single hash mark here. And then after that, let's print out the end of the line, just as before. But now this, of course, is only going to draw a single row. It's going to print out 1 hash or 2 hashes or 3 hashes, but only on 1 line. Let me now incorrectly, but just kind of curiously say, all right, well, if this draws a pyramid of height 1, let's just use ourselves to draw a pyramid of height n plus 1. So the first time I call draw, it will print out 1 hash. Then the second time I call draw, it will print out 2 hashes, then 3, then 4. So we're kind of laying these bricks down from top to bottom. Make recursion. Whoops, I screwed up again. So let's copy the prototype here. Let's put this down over here, semicolon. Let's do this again. Make recursion. All right, all good. /recursion. And now let me increase the size of my terminal window just so you can see more of the output. And here we have. OK, bad, but thank you. So we have an infinitely tall pyramid, and it's just flying across the screen, which is why it looks kind of like a mess. But I printed out a pyramid of height 1, and then 2, and then 3, and then 4. And unfortunately, what am I lacking? Any sort of quit condition, any kind of condition that says, wait a minute, when it's too tall, stop altogether. So this is an infinite loop, but it's not a loop. It's a recursive call. And actually doing this in general is very bad. We'll see next week that if you call a function too many times, you can actually trigger yet another of those segmentation faults because you're using too much memory essentially. But for now, I haven't triggered that yet. Control-C is your friend to cancel. And as an aside, if you're playing along at home or play with this code later, I actually cheated here. We have a special Clang configuration feature that prevents you from calling a function like that and creating a problem. I overrode it just for demonstration's sake. But odds are at home you wouldn't be able to compile this code yourself. But let me do a proper version recursively of this code as follows. Let me go back into the code here. Let me go ahead and not just blindly start drawing 1, then 2, then 3 layers of bricks. Let me prompt the human as before for the height of the pyramid they want using our getInt function. And now let me call draw of height again. So now I'm going back to the loop-like version. But instead of using a loop now, this is where recursion gets rather elegant, if you will. Let me go ahead and execute and code the draw function as follows. Per your definition, if a pyramid of height 4 is really just a pyramid of height 3 plus another row, well, let's take that literally. Let me go back to my code. And if you want to draw a pyramid of height 4, well, go right ahead and draw a pyramid of height 3 first, or more generally, n minus 1. But what's the second step? Well, once you've drawn a pyramid of height 3, draw an extra row. So I at least have to bite off that part of the problem myself. So let me just do for int I gets 0, I is less than n, I plus plus, and let me, the programmer of this function, print out my hashes, and then at the very bottom, print out a new line so the cursor moves to the next line. But this is kind of elegant now, I dare say, in that draw is recursive, because I'm literally translating from English to C code this idea that a pyramid of height 4 is really just a pyramid of height 3. So I do that first. And I'm sort of trusting that this will work. Then I just have to lay one more layer of bricks, 4 of them. So if n is 4, this is just a simple for loop a la week 1 that will print out an additional layer. But this, of course, is going to be problematic eventually. Why? It's not done yet, this program. How many times will draw call itself in this model? Infinitely many times. Why? Yeah, there's no equivalent of quit. Like if you've printed enough already, then quit. Well, how do we capture that? Well, I don't think we want this to go negative, right? It would make no sense to draw a negative height pyramid. So I think we can just pluck off as the programmer an easy case, an easy answer, a so-called base case. And I'm just going to do this. At the top of my draw function, let me just say if n is less than, or heck, less than or equal to 0, that's it. Go ahead and just return. There's nothing more to do. And that simple condition, technically known as a base case, will ensure that the code doesn't run forever. Why? Well, suppose that draw is called with an argument of 4. 4 is, of course, not less than 0, so we don't return. But we do draw a pyramid of height 3. And here's where things get a little mentally tricky. You don't move on to line 20 until draw has been called. So when draw is called with an argument of 3, it's as though you're executing from the top of this function again. 3 is not less than 0, so what do? You draw 2. OK, how do you draw 2? Well, 2 is not less than 0, so you don't return. So you draw 1. Got to be careful here. Draw 1, and now we go ahead back to the beginning. How do you draw 1? Well, 1 is not less than 0, so you don't return. You draw height 0. How do you draw height 0? Wait a minute. 0 is less than or equal to 0, and you return. And so it's kind of like this mental stack, this to-do list. You keep postponing executing these lower lines of code because you keep restarting the draw function until finally one of those function calls says there's nothing to do, return. And now the whole thing starts to unravel, if you will, and you pick back up where you left off. And this is perhaps the best scenario. We won't do it in class, but if you'd like to wrestle through this on your own, using debug 50 to keep stepping into each of those lines logically, you'll see exactly what's actually happening. So let me go to my terminal and do make recursion, which is now this correct version of the code, /recursion. Let's type in a height of 4, and voila, now we have that same pyramid, not using iteration per se, though admittedly we're using iteration to print the additional layer. We're now using draw recursively to print all of the smaller pyramids that need come before it. No, question is, can you only use recursion with a void function? No, not at all. In fact, it's very common to have a return value, like an integer or something else, so that you can actually do something constructively with that actual value. Other questions on this? Say a little louder. When is line 21 getting executed? So if you continue to unwrap, let me scroll down a bit more so you can see the top of the code. So line 21 will be executed once line 19 is done executing itself. Now, in the story I told, we kept calling draw again, again, again. But as soon as one of those function calls, where n equals 0, returns immediately, then we don't keep drawing again and again. So now if you kind of think of the process as reversing, then you continue to line 21. Then line 21 again. Then line 21 again. And as the sort of logic unravels. And next week, we'll actually paint a picture of what's actually happening in the computer's memory. But for now, it's very similar to the pseudocode for the phone book. You're just searching again and again. But you're waiting until the very end to get back the final result. Google now, whom I keep mentioning by coincidence today, is full of programmers, of course. Here's a fun exercise. Let me go back to a browser here real quick. If you've ever gone to, give me 1 second before switching over. Let's see. Give me 1 second. Come on. Sorry. Here we go. I've just gone, well, let's not do this. Let's see, CS50. What's the best way to do this? Apologies, futzing. OK, let's do this so that there's nothing saved here. So here's Google, or here's a Chrome browser. I'm going to go ahead and search for recursion, because I want to learn a little something about recursion. Here is kind of an internet meme or joke. If I zoom in here, the engineers at Google are kind of funny. See why? Ah, there we go. Yes? Yes, this is recursion. And there's going to be so many memes you'll come across now where recursion, like if you've ever pointed a camera at the TV that's showing the camera and you sort of see yourself or the image again and again, that's really recursion. And in that case, it only stops once you hit the base case of a single pixel. But this is a very funny joke in some circles when it comes to recursion and Google. So how can we actually use Google, or rather, how can we actually use recursion constructively? Well, let me propose